So far, we have learned how to find dual linear programming, and we've also seen the economic insight that we obtain from the dual. Now we are going to talk about something that is called dual theorem, but before we are going to the theorem itself, let's talk about something that is called weak duality. So let's start. Let us assume that our primal linear programming is a normal maximization problem, and then our dual problem is normal minimization problem. So the first lemma in weak duality says that if we have a feasible solution to the primal, x, which consists of x1, x2 up to xn, and we also have a feasible solution for the dual, let's call it y, so we have y1, y2 up to ym, then the z value for x is always less than or equal to the w value for y. In other words, when we compute z equals c1 x1 plus c2 x2 up to cn xn, the value of this z must always be less than or equal to the value of w, which is computed in the dual as b1 y1 plus b2 y2 up to bm ym. So let's see the proof. So this is the primal and this is the dual. If we have a feasible solution x in the primal problem, it means that that solution x1 up to xn satisfy all the constraints, right? We start by multiplying the constraints with yi. So the first constraint with y1, second constraint with y2, up to the mth constraint with ym. And then since we know that y must be greater than or equals to 0 from the dual sign restrictions, we will get something like that. X is still feasible, and then after multiplying with y, which is greater than or equal to 0, this feasibility is preserved because nothing is negative, so the sign does not change. Okay, so we just multiply each of the constraint with the corresponding y, and we get something like this. And then we take the sum for all for all constraints. So we have the first constraint, second up to m constraints, and then we take the sum of all constraints. So it becomes like this. The right-hand side becomes the sum of biyi with I from 1 to m because we have m constraints. Okay, so we take the sum of this from I equals to 1 up to y equals to m. So here we have the summation from 1 to m, and then here we have the j that goes from 1 to n because we have n variables. But then for I, it goes from 1 to m because we have y1 up to ym, and also because we have m constraints. Now let's move on to the dual problem. In the dual problem, again, we have a feasible solution y, which means that y1, y2 up to ym, they satisfy all the constraints. Now we multiply each of the dual constraints with x. Because x must be greater than or equals to 0, again, we preserve the feasibility of the dual problem because nothing is negative, so the sign does not change, and then we get something like this. Okay, so basically you just multiply everything with x for each of the constraints. And then you notice that we have n constraints here. So 1, 2, up to n constraints. So as before, we sum all of these constraints from 1 up to n. And this is the result. Now you see that this part, it is the same. Okay, so it's a bit rearranging from xay to become yax because if you think about this, all of these variables, they are just numbers if they have values. So we may rearrange them xay to become yax. It's fine. Okay. Now you can see that this and this, they are exactly the same. So by combining these two inequalities, we may get something like this. So yax must be less than or equal to biyi, and then yax must be greater than or equal to cjxj. So this means that this already proves the first lemma in the weak duality. So if we have x, which is feasible, if we have y, that is also feasible, then the value for the z value for x is always less than or equal to this thing. And then the value for the w value for y, which is this, is always greater than or equal to that thing. If we just ignore this part here in the middle, then we get what is said in the lemma. The z value for x is always less than or equal to the w value for y. So that was the proof, and see how we may use that lemma to see something useful in the relation between primal and dual. So given the primal and the dual problem of the Dakota problem, let's say we have a feasible solution for the primal. So we have x1 equals 1, x2 equals 1, x3 equals 1. You can check that this solution is indeed feasible. It satisfies all constraints. Now the z value for that feasible solution is 110. Now we may use the lemma in the weak duality lemma, which says that the w value for y is always greater than or equal to the z value. So we have the z value 110. The weak duality lemma says that the w value always greater than or equal to 110. And then w is defined by this. So you know that 48 y1 plus 20 y2 plus 8 y3 must be greater than or equal to 110. So if we draw it in a graph like this, if you get the z value for a feasible solution in primal, you know that the w for any dual solution must always be greater than or equals to 110. In other words, it is impossible to find a dual solution that has the z value that is lower than 110. Okay, so now let's take a look at the dual problem. Remember that for Dakota problem, the primal is this maximization. I just moved the dual up here so it is easier to read. Okay, so our dual is this. So let's say we have a feasible solution for the dual. y1 equals 10, y2 equals 10, y3 equals 0. Again, you may check that this solution satisfies all the dual constraints. And then we compute the W for this feasible solution. We get 680. And then from the lemma of the weak duality, we get that the Z value for any X must be less than or equal to 680. In other words, 60x1 plus 30x2 plus 20x3 must be less than or equals to 680. So again, if we draw a graph, we can say that if we have a dual solution, we compute the W, then any feasible solution for the primal must have the Z value less than or equal to 680. In other words, it is impossible to find a feasible solution for the primal that has the Z value greater than 680. Now the second lemma says that if we have x bar, which is feasible to the primal, and we have y bar, which is feasible to the dual, if we compute their objective function value, cx bar for the primal, which is z, and then y bar b for the dual, which is w, if they are the same, then we have obtained the optimal solution both for the primal and the dual. So x bar is optimal for the primal, y bar is optimal for the dual. So here's the proof. For any feasible x, from the first weak duality lemma, we know that Cx must always be less than or equals to Yb. Now, if we have a special x bar, that has the objective function value exactly the same with y bar b, then x bar must be optimal, right? Because Cx is a maximization problem. So we try to maximize this, but it may never exceed y bar b. If it is already equal y bar b, then it's the best that we can do, which means that x bar is already optimal. Similarly, if we look at y, for any feasible y, we know that the value of the value of yb must always be greater than or equal to cx bar. If we have a special y, which is y bar, that is the same, exactly the same with cx bar, it means that that y bar must be optimal. Because remember, our dual problem is minimization. So you try to minimize yb value, and then the best that you can do is make it equal with cx bar. So here we see that if they are equal, means that you cannot maximize the primal anymore. You cannot minimize the dual anymore. It means that we have found the optimal solution for both the primal and the dual. And then they both have exactly the same objective function value. Now there are two additional lemmas which are of limited interest. If you have the unbounded case for the primal, then the dual is invisible. Similarly, if the dual is unbounded, then the primal is invisible. Okay, so let me check your understanding with two questions. So you have seen this slide before. Now, if we have a feasible solution for the primal LP, so our primal LP is this, and the feasible solution is x1, x2, x3 equals 1, and then we compute the z for this feasible solution is 110. Then, based on this weak duality lemma, we are surely able to find dual solution that has W exactly equals 110. Is this statement true or false? The answer is false. The first lemma in the weak duality just says that any feasible y will have the W value that is greater than or equals to the Z value for X, which is feasible for primal. So our Z value here is 110. This just says that for any y, the W value will be greater than or equal to 110. But it doesn't mean that we will exactly find a dual solution that has the objective function value of W equals 110 exactly. If 110 is the optimal objective function value, then yes. But here, if we just have this information, it just says feasible solution for the primal, then we cannot say for sure that we will be able a dual solution that has W equals 110. Now let's say I have a feasible solution for the primal LP, x equals 208, so x1 equals 2, x2 equals 0, x3 equals 8. And then I have also a feasible solution for the dual, y1 equals 0, y2 equals 10, y3 equals 10. And then the statement says they are optimal solution for primal and the dual LPs because z equals w. Is this statement true or false? The statement is true because if you compute the z value, it is the same with the w value. And according to the second lemma, if you have feasible solution for primal and dual that have the same objective function, it means that they are the optimal solutions. So that's the end of this video, and then in the next one we are going to look at the dual theorem. Thank you and see you.